Are there questions from the last lecture? Okay, so last time this is what we did. We said. Okay, we.
Hello, sir.
Yes. Yes.
Okay, sir. I was just reminding you for the screen sharing.
Yeah. I have shared it now. Yes. Last time we talked about generalized eigenvalues. Okay. So in other words, things of the form t minus lambda I times some e v is 0. Okay, so this is what such non-zero vectors. Okay, and we also observed that such a lambda is also a usual eigenvalue, okay, the root of characteristic polynomial. And the other thing that we observed, which will be useful, is that if we take, okay, so this is if so let V inside V be a generalized eigenvalue. Then if we do the following, we start with V, then we take t minus lambda I times V with exponent. I guess we have to fix the exponent, which is okay, with exponent E. Okay. So then we look at V t minus lambda I times V and so on, t minus lambda I times E minus 1V. So these are E vectors, okay, and so what we proved is that this is linearly independent. I mean, I didn't prove the whole thing. I said you should read that lemma in the paper. I've also mentioned the lemma, number of that lemma in the exercises, so you should be able to, so you know what to read. Okay, it's linearly independent and span a T stable, T invariant subspace. So this means that their span, when you apply T, you will stay inside that thing itself. Okay, so this is, let me just remind you what this thing means. That is, if we write W for the span, so we're discussing complex, okay, of V, T minus lambda I, V, and so on, this E vectors that we have, then T little w is in W for all little w inside. That's what we mean by T invariant subspace. Okay, so if you take vectors inside the subspace, applying T won't go outside. Okay, that's all it says. Okay, so this is where we stopped last time. Okay, and so now we want to introduce, go towards this Jordan decomposition. Okay, so first we need to have a notion of a Jordan block. Okay, definition. Okay, D by D Jordan block. Okay, is with for eigenvalue lambda, I mean, sorry, okay, or for or with, I don't know, whatever preposition you like to use. Okay. The point is that it depends on this eigenvalue is the matrix. So I'll write J sub lambda. D will be implicit from the matrix itself. So this, by this we mean an explicit matrix. Okay. So this is okay. So what D is will be clear from the, when you write the matrix, it will become clear what D is. It's the size of the matrix. Okay. So lambdas on the diagonal, zeros. Okay, maybe I should write it in a slightly bigger way. Lambdas on the diagonal, zeros above the diagonal. Okay. So I mean, some books will use zeros below the diagonal. Okay. So this is, but I will just stick to Arjun's notation so that you're not. I mean, if I can avoid using the same notation terminology, I will try. I mean, if I can possibly use it, I will use the same thing. Okay. So this is what. Yeah, and so once immediately below the diagonal, okay, and then zeros below it. Okay, and this is d by d. So such a thing is called a Jordan block of size d. Okay, so we will not often write the size in the notation. It will just become clear from the context. Okay, but lambda we have to keep track because that's the eigenvalue for this map. Okay, so so if you think of J lambda as acting on, so the d by d space is acting on column vectors of size d, then E1 goes to lambda E1 plus E2, E2 goes to, okay. So if we think of, maybe let's just write down explicitly what this means. So for example, J0 could be this, okay, this is 1 by 1, or 0, 0, 1, 0, this is 2 by 2, or 1, 0, 0, 0, and so on. It depends on the size. Okay? But the point is the eigenvalue is a 0. So this is what J0 will look like. So let us say J1 will be just, okay. So J lambda means 1 by 1, it is just be lambda in that, or it could be this. Okay. For the 2 by 2 Jordan block, J1 is okay, and so on. Okay, so this is what they look like. Okay, so what does this Jordan block signify? Okay, so okay, so J lambda.
Sir, just
yeah,
to clarify, all the
yeah,
elements have to be one, right?
on the elements of what to be?
Have to be one, the lower diagonal.
Yeah. So
okay.
The specific matrix is called a Jordan block. Yes.
Okay.
Yeah. And so let us try to understand why that is the way we are. Okay. So this goes back to the calculation we did yesterday. So let us. Okay. J acts on CD. Okay. So this is the d by d Jordan block. Okay. Acts on CD. Okay. By sending E1 to lambda E1 plus E2, okay, E2 to lambda E2 plus E3, and so on. Okay. So the last but one, ED minus 1 will go to lambda ED minus 1 plus ED, and ED just goes to lambda ED. Okay, so this ED is an eigenvector, is an ordinary eigenvector. Rest of them are not. Okay, that is the point. Okay, So inside a Jordan block, there's only one proper eigenvector. Rest of them are this generalized eigenvectors that are not ordinary eigenvectors. I hope. Okay, so that I hope the distinction is clear. Although words like proper or ordinary eigenvector is not, I mean, it's not used in the literature. I am just using those words to make the distinction between, okay, when the exponent is 1 and the exponent is not 1. Okay, so
Sir,
in
here
particular,
here the exponent is d. Right?
sorry, here the exponent is d. Correct. Yes.
Okay, sir.
Yeah. Correct. Yeah. So we can write that out. So yes, I am getting to that point. So what does this mean? Okay, this means that j lambda minus lambda times I. J lambda is this linear operator, linear. Yeah. So actually, I don't know if you have come across this term last semester. Maybe I should just write it because I okay, just okay. A linear map from V to itself is often called a linear operator on V. Okay, so I will, instead of saying let T from V to V be a linear transformation, I will just often say let T be a linear operator on V. So it just means it acts, I mean, it takes V to itself. That's so you want, okay, so that's, so it is, so just because I am likely to use a word unconscious without thinking about it too much. So it's better that I clarify that this is what I mean. Okay, a linear transformation from a vector space to itself is often called a linear operator on that vector space. So this linear J lambda is a linear operator on CD. Okay, and yeah, already I should be using. Yeah. Okay. So here when I say okay, here okay, I already use words that have technical meaning, but which I have not defined. So I hope it's clear. When I say J lambda acts, I just mean this. Okay. J lambda, I mean what J lambda does to CD is specified by this fact. Okay. E1 is E2, J lambda minus lambda I, E2 is E3, and so on. Finally, here, J lambda minus lambda I, E d minus 1 is ED, and J lambda minus lambda I, ED is 0. Okay, I'm just rewriting the previous things. Okay. So this goes back to what we were doing yesterday. We started with one vector, then we repeatedly computed T minus lambda I. Okay. That's what we did, see here. Right? We started with one vector and sort of repeatedly applied T minus lambda I. And that whole thing is a basis and something like this. So this is, okay. So what this Jordan block gives is a basis constructed like this. We are applying J lambda minus lambda I repeatedly to E1, and that would give the rest of E2, E3, and so on. And J lambda has that property. So this is exactly as in that thing. So therefore, the exponent of E1 is D. Okay. Yeah. Okay. So this is yeah. So this is okay. So this is why. So it is. I mean, this matrix precisely captures the sort of relation that we described yesterday. Starting with one generalized eigenvector, we can build a basis for a subspace. Okay. Here it is just for the whole space. So this is okay. So such a thing is called a D by D Jordan block for eigenvalue lambda. Okay. So this is what we. Okay. So this is the building block for this decomposition theorem that we will prove. Okay. So now, definition. Okay. An n by n matrix, okay, is said to be, matrix J is said to be in Jordan form if it is block diagonal and each block is a Jordan block. If it can be decomposed if it is of the form okay, so it is block diagonal okay, so the off diagonal blocks are all 0. Okay, and on the diagonal we have Jordan blocks. Jordan blocks. So some J lambda 1, J lambda 2, J lambda 3, and so on. It doesn't necessarily mean 4. Okay, so it has some block diagonal form consisting of some T blocks, and each block is a of the function, that is J is in block. J is a block diagonal matrix. So I hope you know what block diagonal means. It just means it can be written. It's not a diagonal matrix, but it can be broken into blocks, and only the diagonal blocks are non-zero. Okay. Block diagonal matrix, where each block is a Jordan block. Okay, so this is what. Okay, so for example, this matrix, identity matrix, is Jordan form. Is in Jordan form. Okay, and that is because okay, that is the block decomposition which express it, and each one by one block is a Jordan block for eigenvalue 1. So it has 2 blocks. It has 2 Jordan blocks. Okay. Slightly. So this is true. N by n identity matrix is n Jordan blocks. Okay. So remember, in a single Jordan block, there's a unique eigenvalue. So if you had something like this, 1, 1, 1, then zeros here, and so this is, let's say, 3 by 3. Okay, so this is in Jordan form. Okay, and it has 2 Jordan blocks. Okay, not 3. Okay, 2 Jordan blocks. Okay. And okay, but I just took a special case where all the 3. It has 2 Jordan blocks, but all the eigenvalues are all the same. Okay, and if the eigenvalues are distinct, there must be as many Jordan blocks, at least as many Jordan blocks. So 1, 1, 0, 0, 0, and 2. Okay, this is again in thing and same kind of thing. Okay, so I hope you get an idea what. Okay, so there is.
So this has 3 Jordan blocks, right?
Is what?
The second matrix has 3 Jordan blocks, right? So 1, 1, 2.
Second, no, 2. This is 1 Jordan block.
The third one.
Oh, sorry. Third one is. Oh, I'm sorry. I meant to write a 1 here. I wrote the correct conclusion, but the wrong example. Yes, I meant to write over. Yes, 2 Jordan blocks.
Okay.
Yeah. But on the other hand, if we had a 0, the one that I just erased, if it was a 0, then it would be 3 Jordan blocks. Correct. You're right. Yeah. But in my Okay. So I hope at least it is clear what we mean by a Jordan form. I mean, when we say that a matrix is in Jordan form. Okay? So maybe I should just write suppose we have a matrix like this. Okay, is not in Jordan form. It is very, okay. It is not very difficult to do a change of basis to get this into Jordan form. I mean, to make that is similar to this in Jordan form, but that is, I mean, okay. I mean, that's a separate question altogether. The question is, does this matrix given as it is in Jordan form? That is the question. So this is not. Okay. We cannot, I mean, there's no way we can block, I mean, partition this into blocks so that each block will be a Jordan matrix. Okay, so this is, okay, so this is, okay, so this is the, I hope at least the examples clarify what the definition means. Okay, so now, okay, so then it is easy to write down the characteristic polynomial of a Jordan Jordan block. Okay, so let us say that. Okay, so first of all, yeah. So if you have a block diagonal matrix, then the characteristic polynomial. So all these are exercises in this in this week. If you have already looked at it, you would notice. Okay, if you have a matrix that that can be broken into, so sorry, this is not, okay, so 0 0 here and some a and b here. The characteristic polynomial of this bigger matrix is the product of the individual ones. Okay, so using such things, if you have a matrix that is in Jordan form, it is easy to write down its characteristic polynomial by just looking at the characteristic polynomial of the individual Jordan blocks. Okay, so let us write down the characteristic polynomial of a Jordan block. So this is a, okay, maybe I should just call it A. So let A be a d by d Jordan block. Okay, with eigenvalue lambda. Okay. So then it will look like this. And its characteristic polynomial is just t minus lambda to the d. This is d by d. Okay, so this is okay. So this is okay. So therefore, if you have, if j, therefore, if j is in Jordan form, okay, with Jordan blocks, okay, j lambda 1, j lambda 2, up to some j lambda t. Okay, maybe we should call t, call it r. Okay, so some r Jordan blocks, each one of them looks like this. And on the diagonal, we have these Jordan blocks. Then, yeah, so we also need to keep track of the sizes. Jordan of size d1, dr respectively. Okay, so the first Jordan block is d1 by d1. Next Jordan block is d2 by d2, and so on. Okay, no assumption on whether lambda 1 is equal to lambda 2 or not. That is not really required. Then pj t is, okay, so each one of those blocks we take, so that would be t minus lambda I to the di. Okay. That is the characteristic polynomial of the ith block. Okay. And there are such blocks, they are sitting on the diagonal. So this is just the product. Okay. So this is how the characteristic polynomial will look. Okay. So it's once we have matrix in Jordan form, it is sort of very useful. I mean, it's sort of easy to learn a lot of. To sort of understand quite a bit of properties of this thing. Okay. So that's the reason why we look at it. And for most things,
could you scroll up a bit?
Yeah.
Okay, sir. Thank you.
Okay, yeah. Okay. So for most things, it wouldn't matter what the actual. Sorry. I should probably stay up here. Then I'll come to this. Okay. So please do this. I mean, please keep up with the exercises also, because I'm in parallel developing the notion of polynomial expressions of matrices and when they become zero, etc. Okay. So you should do that along. Okay. I have often restricted the calculations to C, but some of you may have figured out that it has nothing to do with C. But at some point I will clarify. Okay. Maybe after this, at the end of the section, I will clarify why I have, and I put some comments as to why I have restricted to C. Okay. I will clarify what will happen if you remove that restriction. So theorem. Okay. Let T be a linear operator on V, finite dimensional. This is finite dimensional. Okay. Then there exists a basis B with respect to which T is given by matrix in Jordan form. Okay. So the very knowledge of this theorem, as opposed to how to compute the Jordan form, already will get us quite far in understanding properties about linear operators. We'll see. I mean, some of them actually already inbuilt into the exercises. After this lecture, I mean, so by the time we finish the proof, it will be definitely next lecture. So in the next week's exercises, I will add more clarifications as to what. Okay. So just the very knowledge of this. Forget about how to compute the Jordan form. That is typically not easy. Okay. The fact that there is a basis with respect to which the matrix is. So this is I'm thinking about this is field is C. Okay. So that is okay. So just the very knowledge that every complex matrix has this property already will get us quite far in understanding properties about or proving properties about linear operators. Okay. But okay, so this is okay. So that's the reason. So therefore, this theorem is sort of a significant property of linear operators. Okay. We will prove. So I am just going to give the proof in Artin. The advantage of that proof is that it is very linear algebraic. Okay. After you do algebra 3 and algebra 4, you study modules, etc. You will be able to write a quicker proof. But the problem is you have to develop enough material so that the proof then becomes. You will write a different proof, which is substantially quicker. But of course, you have the baggage of developing enough things about modules, etc. before. That is, that can be, that proof is understood. Okay? But we will just follow what's there now. Okay? It is, in some sense, it sort of captures the essence of what calculation must be going on. in proving this. Okay, so this is a theorem. In matrix form, it just says if you have a n by n matrix. Okay, so let me just write it in matrix form, but we will probably just. Okay, let A be an n by n matrix. Okay, then complex matrix. Then there exists P inside GL and C, invertible matrix for thing, such that P inverse AP is. So this is a matrix similar to this one. This is the one that corresponds to change of basis, is in Jordan form. Okay, so these two statements are equivalent. We will just think about it as linear operators. It's easier to prove because, hello, does somebody had a question? Okay, so we'll just probably prove it without using matrix. Of course, we're eventually going to write some matrix. But if you start with the matrix and try to prove it, you know, to keep on doing change of basis, and eventually it becomes unwieldy. Okay, so but if you're abstractly thinking about some linear operator, that's all that we're thinking anyway. So I hope the statement is clear. Okay, and okay. So we will get. So I'm going to start the proof. I will do the first two reductions. And the key part, I mean, where it becomes really, where the technical heart of the proof is when we prove this for nilpotent matrices. Okay? So, so these are all operators. Okay, so we'll say, so let's make that definition now. So I'm making these definitions not for today, but to be used in the proof. I mean, in general, yes, but to be used in the proof next time, in the next lecture. Okay. So an operator is called nilpotent if there is some m such that t to the m is 0. An operator, I mean, when I say operator, I mean linear operator. T on V is nilpotent if there exists some m such that t to the m is 0, that is t composed with t composed with itself m times, acting on a vector v is 0 for all v inside. Okay, so it is to prove this for the nilpotent operators that we would need. I mean, that's where we actually have to do the calculation. Rest of it is just putting together. Okay, but since this is also a technical thing, I will postpone this. So this I will post. So the technical heart of the theorem would be that the proof would be that the theorem holds if T is a nilpotent linear operator. Okay, and from there we will build the full theorem. Okay, so that I will. So the nilpotent part I will do it next time. So it'll also give you some time to think about the definition. Okay, we'll see some examples, etc. So let us do the reductions to the nilpotent case today. And tomorrow, not tomorrow, today is what, Thursday. So next Tuesday, we will do the nilpotent case. Okay, so that's the plan. Okay. So suppose P has a, okay, so proof. So proof, okay. Okay, maybe let us just do one example. Okay, so here is a canonical example of a nilpotent operator, which you already know, but maybe not in this language, which is that. Okay, so let V be the set of all polynomials in CT, okay, such that degree of V is less than or equal to n. Okay, so example. So nilpotent means that if you apply it sufficiently many times to any vector, we will get 0. Okay. So here there are only, so if you do that for the basis, we will get 0. So therefore, okay, but there are only finite, basis has only finitely many elements. So one would get this. Okay. So just this is a vector space, okay, of dimension n plus 1. Then n plus 1 complex vector space. Okay, this hopefully you've seen this example earlier. Okay, and on this I define T to be differentiation. Okay, but I will be little okay. So what does T of little? Okay, so now so this is okay. So what differentiation is this? We just differentiate the exponent. Okay, I mean if you have done complex analysis, you might be when what is differentiation, what is complex differentiable, etc. is a completely different. I mean, it's an entirely different definition. But we're just sort of doing this formally. In other words, T to the E goes to E factorial E times T to the E minus 1. Okay, that's all that we're saying. Okay, so T of A0 plus A1T plus some AD T to the D is A1 plus 2A2 T plus and so on D factorial AD T to the D minus 1. Okay. So just differentiate as if this were real functions. Okay. In other words, sort of formally differentiate a polynomial without worrying about any continuity or anything. Okay. So none of those things we have checked. That this is just like a formal linear operator that we are defining. Okay. We have not proved that this is the derivative, that if you actually differentiate, because we have to actually differentiate, you have to talk about limits, and you have to show that irrespective of the direction, you would not have seen one. Okay, then let me not say that. Okay. Sorry, okay. Already, if you have a function from two real variables, R2 to R, you have to worry about what differential means there, what the derivative means. We are not worrying about any of those issues. This is a purely algebraic operation in which we say that this is what we mean by differentiation, sort of formally differentiating things. Okay, so this is a linear map. Okay.
Sir, it's just D, sir, not D factorial.
Is what?
So the last line, you wrote D factorial, but in fact,
I'm sorry. Thank you. Yes, sorry. Thank you. Here, D. Yes. Yeah. T is a linear operator on V. Okay. And we know that if you apply this n plus 1 times, this is 0. Right? If you take a polynomial of degree n and differentiate it n plus 1 times the way we've just defined, we would get 0. Okay. So this is okay. So in some sense, this is this is an example of nilpotent operator, and more importantly, substantially, our understanding of nilpotent operators can be obtained from this. And we will, okay, so when we prove the Jordan decomposition theorem for nilpotent operators, okay, we will revisit this example and what it means in this example. That would help us understand the proof.
Okay. Hello, sir.
Yes.
Sir, in the definition of V, it should be the degree of F should be less than equal to N, right?
Isn't the word? Oh, sorry. Thank you. I'm sorry for this typos. Degree of, yes, not V. Degree of the polynomial is less than or equal to N. Okay. So that forms an N plus 1 dimensional vector space. And this T that we just defined, sort of formally differentiating, okay, without worrying about the existence of limit and this and that, all those things, is a linear operator, and its nth power is 0. That's all. Okay? So this is an example of a nilpotent operator, which we will revisit when we prove the theorem for nilpotent operators. So this is the crux. I mean, the technical heart of the proof of the theorem is for nilpotent operators. When our first responsibility is to reduce to that case. So let us do that now. So any questions about the so the proof is not going to tell us that if you have a matrix A, what is the P so that P inverse AP is Jordan form? That it won't tell us. It will tell us what the eigenvalues are and what the Jordan blocks look like. But that's, it wouldn't even say that. it would tell us that there is such a P. The proof is not constructing the Jordan form. Okay? So that requires a little bit more work. Okay. Yeah. So proof of the theorem. Okay. So what we want is to bring the problem. So just to keep our this thing in perspective, we might just write down matrices, but just don't think about specific matrices, because then the problem is that we have to keep track of what this P is at every stage. Okay? So instead, we just say here is a T, there is some basis, we just change basis. Then just by saying that, we can get ahead with the proof. Okay. So okay. Now suppose suppose we have some just a minute. Suppose suppose we have this theorem. Suppose we know that this is true. Okay. So suppose we know that T has a basis. I mean, there is a basis. Maybe let us be more specific. So choose an eigenvalue. Okay. Suppose we know the theorem for T minus lambda I. In other words, there exists a basis B for a matrix for the linear operator T minus lambda I. Okay. So suppose that the theorem holds. For T minus lambda I. Okay. That is there exists a basis B with respect to which T minus lambda I is given by Jordan matrix. I mean, matrix in Jordan form J. So this is what we are saying, this for lambda I. So what does J look like? It is sort of lower diagonal. Okay. And the eigenvalues of J are on the diagonal. And then with respect to the same basis, okay, then the matrix of T, okay, with respect to B is J plus lambda I, right? Because J plus lambda I applied to some vector V, the same thing, I mean, times the vector V is the same thing as T times V. Okay, so this is, okay. But if you take a Jordan matrix, okay, and apply the same, I mean, diagonal matrix with lambda. Okay. So this is J itself is like this. Zeros here, and then some J lambda. This is J lambda, let us say. Not lambda. Some J lambda 1 up to some J lambda T. Okay. So something like this. Okay. On this, we are applying lambda, we are adding lambda times I. If you add this, that is also in Jordan form. the block structure has not been disrupted because you're adding the same lambda everywhere, and it's only being added on the diagonal. So the line, so that the line below the diagonal also has not been touched, and the zeros have not been touched. Okay. So that is, I hope that is clear. Okay. So, which is in Jordan form. Okay. So it, I mean, if we added the same lambda everywhere. That is what is that made it work. Okay. If we added it for something else. I mean, if you added different lambdas at different points in the diagonal, it may not be in Jordan form anymore. But okay, adding a scalar multiple of identity doesn't disrupt the property that this is in Jordan form. In fact, I mean, with respect to the same basis. Okay. So therefore, we can conclude it. Therefore, the theorem holds for J. Okay. And why did we do this? The reason is that so therefore so it's enough to prove for J minus lambda I for an eigenvalue, I mean, where lambda is an eigenvalue of I. So now we will replace T by T minus lambda I. Sorry, the theorem holds for I, for T. So we wanted to prove it for T. Okay. We now concluded that if it holds for T minus lambda I for an eigenvalue of lambda of T, then it also holds for T. Okay. And the advantage of doing this is 0 is an eigenvalue of T minus lambda I. In other words, T minus lambda I is not injective and it has a kernel. So that helps us break it down to some smaller dimensional vector spaces. Okay, so this is the reason. Therefore, hence it suffices to prove the theorem for T minus lambda I, where lambda is an eigenvalue. Okay. So now we cannot keep track of this data, so we will just say relabel everything. Okay. We assume that 0 is an eigenvalue of T minus T. Okay, so now, okay, so if we, so or in a more formal way, what the theorem is saying that if we can prove the theorem for all operators which are not injective, which have a non-zero kernel or null space, then we can prove it for every operator. Okay, so that's formally that is what we are. Okay, if we can prove it for the class of all linear operators that are not injective, then we can prove it for the class of all linear operators. This is okay. So this is the okay. Okay, so this is let me just call it step 1. Okay. So by step 1, we have reduced the proof to a case where T, we can now assume that T is not injective. Okay. So now we would like to construct some subspaces, okay, which from this, okay, and then we will try to work with that thing. Okay. Okay. Step 2. Okay. So now we look at the following operators. Consider T, T square, T cube, and so on. Okay. So T, okay, let Ki be the kernel of Ti, T to the I. Okay. So in other words, vectors, the null space. Okay. So now notice that if Ti V is 0, then Ti plus 1 V is 0 for all V in V. Okay. So in other words, Ki is inside Ki plus 1. Any vector that is killed by Ti is also killed by Ti plus 1. Okay? So it's inside this. This is true for every I. Okay. So therefore, this is an increasing sequence of subspaces inside V. So the dimension is, it could be equal. I'm just saying there's a containment. Okay? It doesn't decrease. Okay? So the dimensions will also increase. They're all bounded by the dimension of V. Okay? K1 is the kernel of T. K2 is a kernel. Okay? This is and all of this is less than dimension of V. So because it is bounded, so therefore there must exist. There exist R such that dimension of Ki is equal to dimension of Kr for all I greater than or equal to R. There exists R. Okay. So eventually it has to stabilize because these are integers bounded above by some fixed integer dimension of V. Okay. So this is so there's this one. But what does this say? So remember that we have okay. But on the other hand, so what does this look like? Kr is inside Kr plus 1. This is Ki. Okay, so let I be bigger than or equal to R. So we have this, okay? But they have the same dimension. Okay? So this implies now that Ki is equal to Kr for all I greater than or equal to R. Okay? If you have a vector space and a subspace, and the subspace has the same dimension as the vector space itself, then they must be the same space. Okay? So this is the the containment is just knowing that the dimensions are the same is not enough. That there is a containment is required, and both together will imply that these spaces are the same. Okay. So this is about the kernel. We also look at the image of T. Okay, so let us write Ui, the image of Ti. Okay. So now, image of T square is anyway it's in the image of T and so on. And then and so on. Okay. So in other words, the dimension, and these are subspaces. So their dimension is a weakly decreasing sequence, and it is bounded below by 0. So therefore, it must be it must be some 0 somewhere. It must stabilize somewhere. Okay. Same reason. So dimension of U1 is bigger than or equal to dimension of U2, and all of this is bigger than or equal to 0. And anyway, this is dimension of it. These are a bunch of integers, weakly decreasing, lying between two things. So it must stabilize. So there exists some R prime such that for all I bigger than or equal to R prime, Ui is equal to UR prime. Okay, I'm just summarizing this whole argument. The same. The dimensions have to stabilize, but because there's a containment, the spaces also have to stabilize. Okay, and choosing the bigger of R and R prime. So let M be greater than or equal to max of R and R prime. Okay, so then this holds and this holds. So then Ki is equal to Km and Ui is equal to Um for all I greater than or equal to. Okay, so this is the thing that we want. So this eventually stabilizes. Okay, so then so we will now write K for Km, the stable thing, and U for Um. Okay, and the point is that both of these are proper subspaces. Kernel is proper. I mean, kernel is non-zero because, I mean, of course, kernel could be the whole thing. That's a different thing. But kernel is non-zero and image is not the whole space, because T is a linear operator. By rank nullity theorem, image of U1 is not is less than the image of the rank of U1 is less than the rank of V. Okay, so note that. Okay. Yeah. So U is not V, and kernel is not zero. That's all that we need. Okay. So now we would like, so let's now, before I write down what we want, let us write down, if you're trying to prove, see, we're trying to prove a block decomposition of a linear operator, which means that we can choose bases. Okay, so in such a way like this. So this is an aside. We'll come back to the proof, because in order to justify what the next step and why we are doing the next step, it is better to keep in mind what we want to achieve. Okay, so we are trying, I mean, eventually, I mean, our final goal is to prove we want a basis of V such that T is in block diagonal form. Okay, I mean, that the blocks have to have certain properties is a separate issue, which we'll have to solve, but this is what we need. Okay, so a necessary condition that we are looking for is the following. Okay? So suppose that T is given by, okay, so given by, so any block matrix, first of all, I mean, you can just think of it as two blocks, right? A and B with respect to a basis V1. So let us say this is, I cannot use R, okay, let's just call this thing N1. Okay, V1 through Vn1, and then Vn1 plus 1 through Vn. Okay, so this is the first block is N1 by N1, and the rest is the complement. Okay. So, but what does this mean? So this means that T of V1 is inside the span of V1 through Vn1, right? Because it won't, I mean, because of this zero. This zero here implies this. Right? In fact, it implies this for every similarly, T of Vi is in the span of Vn1 plus 1 through Vn for all n1 plus 1 less than or equal to I less than or equal to n. Right? The same reason that if you apply T to Vi, I lying in the second part, then it won't involve any V1 through Vn plus 1. Okay? So in other words, okay, if you define, okay, so write V1 to be the span of the first n1 vectors and V2 to be the span of the next n1 plus 1 through Vn, the remaining vectors, then V is the direct sum of these two things. Okay. So if we want, sorry, that's not what I wanted to say. And TV1 is inside V1, TV2 is inside V2. That's a point. Okay. V1 can be decomposed as a direct sum of two proper T invariant subspaces. That's what this calculation just said. Okay. So that's what we need to do. Okay, so that will explain what I'm going to do now. Okay, so that is, so let me just write this thing down. V1 is the direct sum of two proper, that's okay, T invariant subspaces. Okay. Okay. And conversely, if V is the direct sum of two T invariant subspaces, then T can be written in block diagonal form. Okay, write the matrix of T with respect to each one of those things, and then put them together. Okay, conversely.
Sir,
Yeah.
so could you scroll up for one?
Yeah.
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 Okay, yeah, so you could scroll.
Is that fine?
Yeah.
Yeah. Conversely, if I'm sorry, not V1, V is the, if V is the direct sum of two proper T invariant subspaces, then the matrix of T, then let A, so let us say two invariant subspaces of dimension n prime and n minus n prime, then let A be the n prime by n prime matrix representing, I mean, sorry, okay. Sorry, I'm trying to write this sentence is going to be very run on, so let me break it. If V is two invariant subspaces, T, so let me just call it V prime and V double prime, okay, then let's just put this one. Conversely, suppose, okay, suppose this. Otherwise, the sentence will be very long. Probably try to avoid it. Okay, suppose that V is this thing. Okay, let n prime and n minus n prime be their dimensions. I mean, they're complementary to each other because it's the direct dimensions. Okay, so let n A be the n prime by n prime matrix of T, okay, for its action on V prime. Okay, similarly, sorry, when I say, sorry, that is not really correct. So you have to fix a basis for V prime. Okay, so let V1 through Vn prime be a basis of V prime, and I just want to label it n prime plus 1 through Vn be a basis of V double prime. Okay, let A and A prime respectively be the matrix of T, okay, with respect to these bases, okay, for its action on V and V double prime, V prime and V double prime. So we are building the matrix, I mean, for the subspaces, and then the matrix of T with respect to the basis. Okay? Then the matrix of T with respect to the if you combine them together, we get a basis for V. So it is block diagonal. Okay? So this is the end of the aside. Okay. So so when we want, sorry, I should not just, okay, I'll just keep it. Sorry, for scrolling. Okay, I'll just say, see, what we want is eventually to get T in a very nice block diagonal form. Okay? And getting it into any block diagonal form requires us to think about T invariant subspaces. Okay? And then trying to write the matrix on the invariant subspaces. Okay, so that is what we are going to prove now. Okay, so yeah, okay, so I hope this is. I mean, what I'm going to write now is clear. Would be clear. The context of it would be clear by this remark. Okay. Okay. So now we are back to the proof of the theorem. Okay. We will prove that K and U, I mean the eventual stable value of the kernels and the eventual kernel stable value of the images. Okay, we will prove that they are T invariant and that they form a direct sum, and the direct sum is T. Okay. We will show that okay, K and U are T invariant subspaces. They're of course subspaces. Okay, so let me state this. I will go back to the definition of K. Okay, and that V is K direct sum U. Okay, so then we can work with T restriction to K, T restriction to U, build the individual matrices there and put them together and get the matrix for V. That is what the aside remark was saying. Okay, so okay, so that is. I hope the context for trying to prove this intermediate step here is clear as to why we are doing this. Okay, so just to recall, what is K and so Ki's are the kernels of the successive application of T, so that will become a stable value. Okay, so Ki is, I mean, for all sufficiently large I, Ki is equal to Ki plus 1. Similarly, Ti is Ui is the image of this thing, and they have a decreasing thing, and so for all sufficiently large, they'll be the same value. And the stable value of Ki and stable value of Ui, we call it K and U. Okay, so this is what they are, of course, subspaces. Okay, the question is T invariance and the direct sum. Okay? So suppose so let V be inside K. What does this mean? This means that for all sufficiently large I, Ti, I mean V is in the kernel of Ti. Okay? So therefore, T of V, I mean T, I mean if you take T of V, I mean T of I to T of V, and I again is 0 for all sufficiently large I. I mean, this is just T to the I plus 1 V. But if T to the IV is 0, then this is true for Ti plus 1 also. Okay. But of course, this is true. I mean, we need this for every sufficiently large. So therefore, T is right. So therefore, T of K is inside K. I mean, K is a set of vectors satisfying this property, that for all sufficiently large, this thing. And TV also applies that, satisfies that property. So Tk is inside K. Okay, so that is K is a T invariant subspace. is. Now, what about the image? Okay. So now remember, T apply to, I mean, UI, or in our case, we will take UM specific to that thing. It's easier to argue for that thing. Okay. UM itself is the image of the application of T to the M times. Okay. Note that. Note. UM is U, which is UM, is the image of TM. Okay. Okay. Therefore, UM plus 1, okay, which is also equal to U. U is a stable value, and from M onwards, it all has the same value. Okay. This is equal to T of UM. Okay. And that's what we wanted to prove. T of U, I mean, what we wanted to prove is T of U is inside U. But T of U is same thing as T of UM. Okay. But T of UM is UM plus 1, which is U. Okay. So this is, okay. So therefore, U is T invariant. Okay. So now we have got two candidate T invariant subspaces. Okay. So we just have to check that we can prove this for K is a direct sum. Okay. So I think I'll stop after that, because we need to also look at what happens to T restricted to U and T restricted to K, but that will go over time. So it will also not be done in. Yeah. Okay. So I would like to take some time to explain that. So okay. So we'll just stop by showing this. Okay. And then we'll pick up from here in the next lecture. So please, before you come to the next lecture, please make sure you read it, because I'm just going to continue. It's a long proof. So it's difficult to summarize. I mean, it'll take time even to summarize the key points of the proof. So I will just use a notation and continue. So please make sure that you read the proof and the notation is clear in your head before the next class. Okay. So here is T U invariant. Okay. So now suppose we need to show two things. Okay. We need to show that so kernel. I mean, what is U? What is U? U is UM. Okay. It is the image of T to the M. U is image of is UM, which is the image of TM, and K is KM, which is kernel of TM. Okay. By rank nullity theorem, dimension of U plus dimension of K is equal to dimension of V. Okay. So if you prove that they don't, I mean, they have trivial intersection, then they must generate the whole space. Okay. So therefore, to prove that, to show that V is U direct sum K, it suffices to show that U intersect K is 0. Okay. So remember, U direct sum K means U plus K is V and their intersection is trivial. U plus K is V comes from the rank nullity theorem. I mean, and U intersect K, we have to check. Okay. So now, okay. So let U. Okay. So let V belong to K intersect U. Okay. Remember, this is equal to Km and this is equal to UM. Okay. So there exists. Maybe I'll call it something else. Let's call this thing W. Okay. There exists V in V such that W is Tm of V. Right? Because this is UM. It is UM. Okay. Okay. So this is Tm of V. Okay. but W is inside is inside K also. So if you apply T to W, then we would okay. So we want to show that W is 0. That's what okay, that's what we want. Okay. So let us now apply T to the 2mv. This is just T to the m times W. This is 0, right? Because W is in the kernel of 2 to the n. Maybe I should write it this side. Okay. So in other words, therefore, V is inside K2m. Okay. Okay. But this is the same thing as Km. Okay. This implies now that T to the mv is 0. That is, W is 0. Okay. So this proves just that we have now broken V into two T invariant subspaces. Okay. So we will now look at T restricted to U and T restricted to K. Okay. So we'll use the observation that we made earlier. T is not surjective. Therefore, U is a proper subspace of K. Okay. And V is not 0. So therefore, I mean, K1 is not 0. So therefore, K is also not 0. Okay. So these are actually proper subspaces. I mean, it is possible that K is the whole space and U is 0. That is okay. Okay. But eventually, we will have to now worry about T restricted to K. That's where the nilpotency comes in. Okay. So that we will do next time. Okay. Any questions? Okay. Yeah. So please do. I mean, you don't need to read the full proof. I mean, you don't need to read ahead in the book, but you should at least be clear. I mean, at least have the notation itself, at least a basic reasoning in your mind before the next lecture. Okay. So please do read my notes before that. Okay. I'll stop here.